I can go ahead and email that to you if you'd like, Dr. Trom.
Okay, well, I just hit record too, so I'll probably get my own separate recording. I hope I will. We'll find out the hard way. All right, so let me turn the floor over to group 637U to describe the CycloTracker Heliostat.
All right, hello everyone. As was said previously, we are group 637U, the team Dyson Sphere, and our heliostat is called the CycloTracker heliostat. Next slide, please. So first thing I'd like to jump into is our house equality analysis. So we picked from a list of customer requirements, which is what the heliostat needed to do, and we picked 7 of what we thought were the most important, and that's what you can see on the left-hand side. In the upper part of the house equality is our design requirements, and what those do is we come up with a list of design requirements that help us achieve those customer needs. For example, having a low cost budget, and so the design there would be designing for the cheapest module costs, for the cheapest material that still gets the job done. And so as was said previously, we went through some of the old EML4502 or 4501 designs, and we picked 4 that we thought were the best. And so we compared them up against a baseline model that was created this semester. And going through the process, we ended up picking that baseline model. And later on, we will make some modifications to this baseline. And some of the customer needs that I want to make note of that we really focused on this semester are the ability for the heliostat to survive under weather conditions out in Las Vegas, since that is the location of where these heliostats will be placed. The ability for this heliostat to survive for 20 years. Our module cost, or sorry, our material cost under $110, and the ability for our heliostat to track the sun's rays by rotating on 2 axes. All right, next slide, please. And so the next thing I would like to get into is our hedgehog concept statement. So our heliostat captures both the sunlight and the group's dedication to quality, safety, and performance. And this will be seen throughout our design. Next slide.
Okay, so that baseline design that they were talking about earlier is shown there on the left, and on the right is our final SolidWorks model after all of our design changes. So as you can see, there are a couple of structural changes to say the mirror mount and things like the base. But 2 of the main changes that I wanted to highlight are the change from a PET-G column in the center to 2 45-degree PVC pipes, and as well as the change from a harmonic drive to a cycloidal drive. Next slide, please. So I'm just going to go a bit on to our subassemblies. So the first subassembly is the motor mount assembly, which is a 45-degree inch PVC pipe connected to our PET-G mount and held in place through adhesives, as well as a pin that keep it mechanically in place. The second subassembly is the cycloidal drive assembly, which we will get into more detail later, but it's that, as well as some PET-G parts used to connect the 2 pieces of PVC together, as well as a NEMA 17 motor. The unlabeled portion is just another PVC pipe, and the base assembly is again the same cycloidal drive assembly and motor, as well as a very similar PET-G base. However, the only difference between the 2 is a 1/4-20 screw in the bottom used to connect it to a mount, and the giant box there, which is a placeholder. We really didn't get into the electronics this semester, and so the actual final design would have that box be quite small. Next slide, please. So one of the main things one of the more significant things we changed was the PET-G to the PVC Center Supports. That was part of our ongoing desire to try and have as many OTS parts as possible. And we were able to determine that the PVC would be able to meet all of our design requirements. It's also relatively cheap and significantly quicker to acquire than the PET-G, and is also is waterproof and resistant to most acid, salts, corrosives, and so on and so forth. It also has a max operation temperature, 3 degrees higher than the highest ever recorded temperature in the Las Vegas. So it should be fine there as well. And the main issue with degradation over long periods of time is that it becomes much more brittle. However, if you'll look at the graph on the left, the modulus of elasticity and the tensile strength don't change nearly as much. And considering that the main source of degradation is the UV light or UV radiation, painting over the part as well can be used to prevent that at a cost. Next slide, please.
Yeah, so getting into more of the cycloidal drive assembly, our design utilizes a cycloidal drive, which is a gear drive, which ours utilizes a 48:1 gear ratio, which converts a high motor speed into a large torque. The reason we chose to switch to a cycloidal drive rather than a harmonic drive that the baseline model has is a harmonic drive uses flexible parts or like a flexible belt to get that gear reduction motion. And this uses all either OTS bearings or rigid parts. So getting more into the assembly that we see on the bottom right, we see an exploded view of the assembly. And on the top right, we see an animation just gotten from Wikipedia of how this cycloidal motion kind of acts. Essentially, we have 49 dowel pins and our cycloidal gear has 48 teeth. So that reduction in teeth, like one less tooth than the number of pins, allows us so that when the cycloidal drive rotates, or when the motor rotates one full revolution, the cycloidal drive rotates one tooth in the opposite direction. And that gives us our high gear ratio. Our design utilizes 3 bearings, 1 thrust bearing and 2 roller bearings. One of the roller bearings is placed inside of that cycloidal gear, and it's placed at an offset, kind of like you see in the green pin in the animation on the top. And that gives that eccentric motion. And the second bearing keeps the torque extract plate centered, which is that top hat looking piece in the exploded view. We see that torque extract plate has 6 holes in it, and those are 6 M3 holes. 3 M3 screws are screwed into the back of that, and those kind of act as those purple pins in the top animation. And then 3 more M3 screws drill into the other side, or screw into the other side, and that attaches to another 3D printed part that attaches to the PVC. Our design has no back drivability, so when you put a force on the gear, there's no give, and it utilizes only 3D printed parts, OTS bearings, and we decided to have that torque extract plate actually manufactured to be metal because that's the part that undergoes the most load and holds the fasteners. Next slide, please. So here we have a short video just showing the internal motion of the drive. It's a bit stuttery, but as you see, that center white piece stays stationary. It just rotates about the center of the motor, and the blue gear kind of has the motion we saw the yellow gear in the last animation have. And in this video, you could also see the limit switch on the left that we essentially use to home the 45-degree PVC elbow. Next slide, please. So one limitation of our design is that due to the geometry of our heliostat having 2 45-degree elbows that rotate about a bottom connection, the mirror will always miss a point light source that's coming straight down. Additionally, due to the high gear ratio, the motors are powerful, but they move very slow. Now in the real world, this isn't really a problem because we are tracking the sun, and the sun isn't just like a point beam coming straight down, and the sun moves very slow. So these are only problems we had during testing. One unavoidable design flaw is that due to the use of limit switches, each PVC elbow can only make 1 full revolution, and due to the cycloidal motion of the gear drive, there exists a sort of stepping motion when the motor rotates, making it a bit difficult to calibrate. In future iterations of the design, this motion could be reduced by adding another cycloidal gear in that gear drive assembly basically offset 180 degrees to kind of counteract the cycloidal motion that persists. Next slide, please.
So after we kind of nailed down the structural aspect of our design, we went ahead and tested it to make sure that we meet the design requirement listed in the customer needs statement, which is that the design is fully operable in the target installation site, which is Las Vegas, at a required factor of safety of 2. And so we conducted this test for the static version of the full scale heliostat. So that means it was kind of mid-development in terms of programming, but structurally it was aerodynamically representative of our final model. So we physically locked down the heliostat using a quick release plate on the bottom of the base, and we put it through a series of tests in different mirror configurations at different wind speeds. So we performed tests at basically 2 mirror configurations. The first one was at normal operating conditions, which is where the plane of the mirror is perpendicular to the oncoming air, which simulates a high drag, the highest drag coefficient that it's going to experience. And so we tested that with an industrial fan at low and high speeds at a range of about 9 to 12 miles per hour, which is the average wind speeds in Las Vegas. And the heliostat was subjected to each of those speeds at that configuration for 5 minutes, which is 15 full rotations. And the passing condition was basically that it passed if it didn't catastrophically fail. And the second test we performed, the second configuration was basically in safety mode, which is what you can see in the video right there, where the plane of the mirror is parallel to the oncoming air, which simulates the lowest possible drag coefficient. And we used an electric jet fan blower, which blew air at around 140 miles per hour to test that required factor of safety of 2, and it had the same passing criteria. And basically we passed both tests. So structurally, our design met that design requirement, and it can survive the worst case weather conditions in the installation condition or location. Next slide, please. So this is just a list of our bill materials. And basically we try to use the same kinds of fasteners wherever possible in order to minimize the number of parts. And we also tried to use OTS parts when we could, which is why we repurposed the PVC and kind of used the modified PVC elbows and incorporated that into our design. Next slide. And the total cost for all the materials that we need for a single module came out to be $90.32, which was significantly under the given budget of $110. And for 3,000 modules, which would be a whole field of heliostats, that would cost about $271,000.
With our code, we can individually move each motor using the step move, azimuth, and elevation functions. With the step and move functions, we can move the motor by the number of degrees or steps inputted, whereas with the azimuth and the elevation functions, it moves to a specified location inputted by the user. We also have a danger function, which moves the heliostat to a safe position in case of an emergency. We have a temperature function, which outputs the temperature and humidity of the electronics box. We have a power function, which enables and disables the motors. And we have a homing function, which moves the heliostat to an origin dependent on the location of 2 limit switches. Next slide, please. For the motor control test, our step and move functions were tested to see if we could move the heliostat forwards and backwards. Our homing function was tested too, and that went fine. We only had an issue where our motor microcontrollers got really hot. So we put heat sinks, and that really helped with that issue. Next slide.
Sweet. Once we verified that we were able to move the motors in both directions, our next step was quantifying the geometry of the heliostat so that we could train it on a given target. So due to the geometry of the CycloTracker involving the 2 45-degree elbows, simply using trigonometry to define the inverse kinematics of the system was really not practical, especially because the motion of that top motor affects both the azimuth and elevation angle. So that was kind of the first issue that we ran into. To get around this, we had our own solution. We defined the geometry of the heliostat using Denevit-Hartenberg parameters, and essentially these parameters allow you to set up a set of reference frames that can transform you from the origin to a desired point, which in this case would be at the center of the mirror of the heliostat. So using this forward kinematics method, we were able to basically use brute force to solve for all possible angles of rotation and reach the correct location during the laser targeting test. So I'll dive more into the kinematics here. Essentially, these DH parameters allowed us to go from the origin to the center of the mirror. We performed another transformation going from the origin to a point, an arbitrary point 1 unit in front of the center of the mirror, which allowed us to create a unit vector coming out of the center of the mirror. And let's see, sorry. After that, we defined that unit vector and we used that for our optics calculations, which was allowing us to find the angles needed to have the proper reflection from the incoming laser beam to the point on the wall that was desired. So in order to do that, we were looking at some optics equations here. And essentially we found that the angle between the incident ray, which would be the laser ray coming in straight down from the laser, and the angle to the reflected ray should be perfectly equal, meaning that the normal vector coming out of the center of the mirror should bisect those two rays. And we used some optical calculations here, some vector projections, and we were able to find where that ideal normal vector should be in space. Using our brute force method and our forward kinematics, we're able to loop through all of the possible angle solutions, find the 2 angles theta of both of the motors that led our normal vector to be in the proper configuration to basically cut down the center of both of those rays. And we use that to determine where we needed to put our heliostat for the laser targeting test, which we'll dive into in just a second here.
All right. Hey guys, so following the relevant kinematics and optics calculations, we can now come upon the laser reflection and targeting test. So this test is essentially going to act as the final step at this stage in EML4502 and then the entire heliostat design process. And it's going to emulate the field environment where it would be operated under inside the laboratory while ensuring the design meets the customer accuracy requirements. So a few things we had to consider before we got to the actual test include some issues that Daniel discussed earlier, such as the 45-degree elbow design with the vertical point light source, as well as that donut-shaped circular zone in which the light source can't really strike the mirror directly. So these issues were mainly fixed by the use of that mobile laser scaffolding, as well as a fixed mount on the table for that quick release bracket. And having that fixed mounting point is also going to reduce the need for error and recalibration when conducting the test multiple times. And keep in mind that while these issues really only pertain to lab, having it outside in the sun is going to be a bit more forgiving accuracy-wise. So next slide. So onto the test itself, it's going to consist of reflecting the laser onto 5 targets mounted around the lab. And that's going to have to fall within a conical angle precision of about plus or minus 0.5 degrees. And in addition to the actual laser targeting, we're going to have to run various commands that Maria also went over, such as powering down and temperature monitoring, among others. So building off of what Brandon was talking about, in order to relate the theoretical motor angle values with the actual heliostat values, we had to make a correction factor. And that turned out to be approximately 10 degrees for the bottom motor and 1 degree for the top motor. And after finding this transformation and using that, the correct angles were determined and we were able to reflect successfully onto each of the 5 targets. All right, next slide.
So to summarize, our design really has a lot of benefits to offer if it were used for any future Mech 3 classes and anything beyond that. The cycloidal drive really provides a compact solution to drive the motion of the heliostat, and it's still able to accurately track the light source. And the drive can also be assembled and maintenanced independent of the design. So those smaller, more fragile parts like the gear, the torque extract plate, all of the bearings are the most susceptible to wear and damage. And so enclosing that really extends the lifetime of the product. In terms of cost, our design is also significantly under budget, which leaves a lot of room for future Mech 3 students to kind of optimize the design and play around with it. And it also uses modified OTS parts. as opposed to an entirely 3D printed design, which significantly reduces manufacturing time. And it also, since it's a fully enclosed design, so all of the internal components are inside of the PVC elbows, it overall lengthens the lifetime of the heliostat. So there's a lot of room for additional development, but overall our design really gives a solid baseline that is capable of performing the accurate tracking while minimizing cost and optimizing space. Thank you all so much for joining us. And do you have any questions?
All right. Thanks for the presentation. People are chiming in on chat. Great work, guys. Some applause from the audience. In parallel, do we have any questions from our panel?
Hey guys, this is Tom Singer from Northrop Grumman. The actuation mechanism here is very different than things we've seen in the past. I'm kind of wondering what the trade study was that led you to this as opposed to something more conventional.
So we were really researching what kind of mechanism we could use to actually output that high gear ratio that we wanted, because our PVCs were kind of heavy, and the low cost and high torque output of this design that is a modified design of something that we found online really came out to be just the best. So we essentially took the design from this guy's online source, modified it so it had the right pin diameter, it had the right torque output that we needed, it had the right gear ratio, and we applied it to our model.
Can you speak to complexity of manufacture, the lifetime of components in the field, those sorts of possibly negatives, possibly just things to think about?
Yes, regarding manufacturing, this design does require tight tolerances. We were getting some issues trying to change some of the gear ratios with there being some backlash or some stalling on the motor. So making sure the design is manufactured with tight tolerances is important. As for lifetime, we weren't able to test this years on end, so we don't exactly know the numbers for that, but with further testing, that is definitely something we can look into.
Okay, I would say things that require long lifetimes that are, it looked like you had pins sort of sliding around in holes. That says wear to me, right? And so, there are going to be concerns with that for the lifetime. I think you'd mentioned that you were needing to add another one of your gear systems in order to better control positioning. I think you'd mentioned that earlier on in the presentation, which is going to add further complexity, further cost. So I like it. It's something different, and after sitting through a dozen of these, it's nice to see somebody thinking along different lines, but it certainly raises some concerns. The other thing I'll pick out is on your wind speed test. You had mentioned that you were showing a factor safety of 2. How do you come up with a factor safety of 2?
I think in the customer design requirements, they asked for a minimum factor safety of 2 for all the components.
Okay, so what does that mean?
I guess in our case, it would be sort of speaking to the load applied.
How much more load did you apply than nominal?
I guess we don't have a factor, a specific number to give you.
So from the customer requirements, if I am remembering correctly, the worst wind conditions that we were supposed to be expecting was for it to survive up to 70 miles an hour. So
okay.
for the wind survivability test, we that's where the 140 came from. It was for the factor safety.
All right, so you doubled the wind speed. What did you do to the loads? If I remember, drag equation goes with v squared.
Yeah, we didn't do a lot of extensive testing on loads specifically throughout the semester. I'd say a big focus of our time with this design is definitely focused on the proof of concept. And as future semesters go through, it's going to be a large focus on survivability and specifically like wear and tear on components, like you mentioned. So that's something for future classes to look into, but we didn't exactly like have a lot of that within our specification for this design.
Okay, good. That's the answer that I wanted to hear is essentially that this is a prototype focusing on the kinematics and mechanism and not so much on structure, right? And I've kind of gone off, and I think Dr. Traum's getting tired of hearing me say it to other groups, like, you know, people doing structural analyses and saying this can withstand 140-mile-an-hour wind that we put a leaf blower on it. Like, that doesn't really relate to what the ultimate product is, which is going to have a significantly bigger mirror and all the other sort of considerations that go along with that. So I'm glad to hear that specific answer.
So
real quick, I just wanted to mention, you mentioned something about the pins like sliding into that PV or into the PET-G housing for the cycloidal drive. I forgot to mention it earlier, but the purpose of those pins is to create a better sliding surface for the internal gear of that cycloidal drive to like rotate against, because if it's just PET-G sliding against PET-G, that creates a lot of wear over time. So that was the purpose of implementing those pins.
Sure. Yeah, certainly a metallic pin there is probably preferable than plastic on plastic, but even that over a 20-year lifetime of a system, I think is a concern.
Yeah, and definitely we could look into instead of having these parts being 3D printed, being actually manufactured into metal parts.
So I did want to mention, since Tom, I've finally managed to read through and distribute the feedback in the email that you sent earlier from yesterday's presentations. So the wind test, kind of weird, right? Like why would we do a wind test on designs that are very clearly smaller and at least mirror size. So I have to admit, and now that the semester's over, I can kind of reveal this. I had an ulterior motive for the wind test, right? It was, sort of a cool thing to put the heliostats into a wind tunnel and blast them with a leaf blower. But my real pedagogical intent for doing that was to force is the wrong word, but to compel the students to create like a non-functional mock-up of their prototype. So that was like, so initially the assignment didn't have anything to do with the wind test, and we were sitting around in a teaching team meeting, and I'm like, yeah, I want to see like, non-functional mock-ups, and all the TAs are looking at me like, that's boring, nobody's going to do that. Like, so we sort of invented the wind test as a way of compelling the students to create what we described as a aerodynamically similar design to their final design. And it worked. Every single group got their designs completely mocked up, and we threw them in the wind tunnel and they were tested. And so it did have an alternative pedagogical purpose that probably was more meaningful than just testing for wind survivability, which was to get every group to that point of having a non-functional mock-up by that point in the semester. So anyway, now everybody knows why we did the wind test. So on that note, any other questions from the panel?
Hi guys, I just wanted to say I like that you used your creativity and chose something different, and I liked that you had really good graphics and diagrams. I was just wondering, why did you choose the 45-degree angle design? It did make it kind of difficult for you to do the calculations on the kinematics, but yeah, I applaud you for working that out.
In all honesty, that design choice was somewhat arbitrary. We were just going off the baseline model, and we realized later in the semester that made our lives more difficult with the kinematics and all that, but it posed a challenging problem that we were able to work through.
Yeah, to add on to that, initially we selected that baseline design with the 45 angles because we liked that it enclosed all the internal components, whereas the other designs from the previous Mach 2 class had all these exposed gears and bearings, and we didn't really want to get into that territory. So we liked everything was kind of in one product, one design.
So the baseline design is from a past semester?
No, that was a design that was introduced this semester.
Yeah, I'm fairly certain like one of the TAs came up with it and like proposed it to the class as one of the optimal designs that we pitched against like the other designs that were analyzed through previous semesters.
So this was a new just this semester. Okay.
Yeah, we had Noel Thomas, who's our teaching technician, who is a former Gator Motorsports president, has been basically instructional technician for the past several years. We put him in isolation. We just put him in a room and we said, if you were to design a heliostat to address these customer needs, not knowing anything about any of the other designs, what would you come up with? And that was the design that he came up with, was the non-orthogonal, everything enclosed, harmonic drive, like print in place, like basically every bell and whistle that he could possibly pull out of thin air, he put into that baseline design. And then honestly, again, since I'm putting all my cards on the table, when he presented it to the class, I was 100% convinced that not a single group would pick it because it had so many like untested, unproven, very difficult to implement elements. And yet, as we've seen, a subset of the groups in the class actually went with it. And I don't think any group ended up using all of the features that Noel had originally designed, but they found things like the harmonic drive, for example, wasn't giving them the reliability they wanted. And so some groups went to planetary gear drives. These guys used the cyclotral drive. So groups made little modifications to that original baseline to make it viable, but that's where it came from. It was one of our technicians just sat down and catted it up in a couple of days, just to provide something as a starting point for the students to do their house of quality analysis against.
Okay, thanks.
All right.
I'm just wondering, oh, sorry.
Oh, no, go ahead.
What was the total number of parts in your design?
I'll pull that up real fast. I want to say it's somewhere around 37. Let's see, 27. There we go. 27 individual parts.
But you have 98 pins.
Oh yeah, and Daniel, you can go more into that. That's to provide the gear reduction ratio in each of the drives. And I don't know if you can see them in the video. Let's see. Go back.
Yeah,
what
that's
is the assembly time for this?
I think Will had that pulled up, maybe.
I remember it being
Assembly time wasn't something. Yeah, we didn't necessarily quantify it yet. It was definitely a lot of trial and error in our case, getting to the final design.
Took us about an hour to build it ourselves, thereabouts, from start to finish. And that was actually the cyclotral pin that were one of the things we would change if we had to do this design again, because we actually worked about trying to drop it to 11 pins during the semester, just switching out the cyclotral drive and having it have a much smaller gear ratio, but also be able to not take as much time and components to complete. And what we found was actually it would start to slip at those smaller amounts of pins. So if we were to improve on this concept, we would probably try and find a happy medium between the two.
Yeah, specifically the reason for that slippage, I realized after, was because the pin size we were using in like as a ratio compared to the amount of pins we were using, the pins were just way too small. So if we used like some bigger surface for them to contact, that would create like less room for that internal gear to slip. So there is a workaround to these problems if we wanted to change the parameters such as the pin size, the gear diameter, or whatnot.
Great. I like that you identified the lessons learned and improvements you would do on a next iteration. Thanks.
All right. So we've run significantly over. There's actually meant to be a break, a 20-minute break that we've completely consumed. So let's maybe call it quits there. Let me hit the record button here.